Hi everyone, my name is Jerry Bartles and I am a Technical Marketing Manager here at Autodesk. I'd like to welcome you to today's presentation where I will be providing a technology review of the Autodesk Vehicle Tracking Solution. During this 30-minute demonstration, we will focus on several key aspects of the planning and design processes used on transportation and site design projects. These include the ability to accurately predict the movements of steered vehicles. This includes cars, trucks, service vehicles, airplanes, and more. Essentially, when our project is finished, it will need to accommodate a number of different vehicle types. As a result, it is important to ensure that these vehicle maneuvers can be analyzed throughout the design process. We will also look at the importance of optimizing road and campus geometrics. At the end of the day, the project owner seeks the best design solution possible. To attain this, we will need the ability to quickly evaluate design alternatives. Finally, we will review the significance of being able to perform real-time analysis. Essentially, how quickly can we get the information or feedback necessary for us to make our next design decision? This also plays into our adherence to design standards. In other words, as we make each design decision, we need the ability to confirm that it complies with accepted design standards. Now, the way we will focus on these areas will be through a brief demonstration, followed by a summary with some time left over for Q&A. Now, my goals for our session, well, I want to give you some exposure to the Autodesk Vehicle Tracking Solution, as well as review a subset of its capabilities. Now, I say subset because it would take much longer than our 30 minutes to review all of its functionality. Instead, we will focus on several primary features, and we will do it through the lens of its business benefit. In other words, how specifically does Autodesk Vehicle Tracking improve the planning and design process? And finally, I want to ensure that we address any questions you have about our solution. So with that, let's go ahead and get started. We begin with a project where, like most projects, we need to evaluate if our geometrics can support a service vehicle. In this case, it's a standard school bus. Essentially, we need to confirm if a school bus can successfully maneuver from the southwest through our project, exiting at the northeast. Using Autodesk Vehicle Tracking, we can determine this very quickly. First, we will start by selecting Auto Drive and then choosing the appropriate design vehicle. As we do this, I would like to point out the extensive vehicle library that ships with the solution. It contains design vehicle definitions and types from across the globe, numbering well over 1,000 vehicles. For our project, I will select the standard 65-foot school bus from the U.S. AASHTO Design Library. Once selected, we can use the vehicle diagram to see specific information about the selected vehicle, including dimensions, as well as a chassis view and profile view. From there, we will proceed by simply clicking points within our project roadway and literally drive the route we would like to evaluate. As we pick points, you will notice a green and red envelope being constructed. The green outline indicates the envelope created by the vehicle body, and the red outline indicates the envelope created by the chassis. Using this outline, we get immediate feedback as to the horizontal space required to maneuver our vehicle. As we enter the roundabout, maneuvering is a little more challenging, so I'll pick my points a little closer together. When finished, a number of intelligent grips are displayed. Using these grips, we can easily edit or refine our vehicle path. As we make changes, the results are dynamically displayed. And if we make an adjustment that results in a maneuver that our vehicle can't physically do, we get immediate feedback in that the envelopes terminate at that point. Now for our project, the resulting swept path analysis shows that a bus can make the corner so long as the brick area is a surface designed to be driven over. To complete this process, we would go back and review the entire path and make any revisions as necessary. Now by using the intelligent grips, these revisions could involve adjusting or creating target points. With our swept path analysis complete, we have confirmed that it works horizontally, but there's more that should be considered. By performing a design check, we can evaluate our vehicle path against a number of rules-based constraints. In our case, the results show that we have a severe steering warning, and what that indicates is that our maneuver requires a steering angle that's in excess of what is permissible. For further detail regarding steering, we can easily create a graph within our model. Once created, Autodesk Vehicle Tracking displays steering limits as well as the steering angle throughout our swept path analysis. Looking here to the right, we can see the area where we exceed what is currently permissible, and that coincides with our maneuver through the roundabout. Using Autodesk Vehicle Tracking, we are able to quickly and easily determine if our design can accommodate vehicle movement, as well as confirm if that movement complies with rules-based constraints. Now, because vehicle movement will also involve negotiating a site, let's take a look at another example. In this situation, we want to confirm that our design is such that a 30-foot rigid delivery truck can successfully access the loading area of this commercial facility. Like our last example, we will begin by selecting Auto Drive and then choosing the SU30 design vehicle. However, this time, rather than picking each target point to drive through within our design, we'll let the system compute some of the path for us. We can accomplish this by starting our swept path and then choosing an alignment to control our turns. The first alignment entity we choose will be the entrance centerline stripe. We will then select the edge of pavement parallel to the building, and we will finish by choosing the pavement edge near the loading bay. In literally 4 clicks, we were able to accurately complete our analysis. Like our prior example, we can now use intelligent grips to refine our swept path analysis if necessary. Within the parking area we seem to be okay, but if we check the drive entrance, we see that the tires of our truck will leave the roadway. Now in the real world, a driver could resolve this by performing a steering overturn, and by clicking the arrow grip, we can simulate this maneuver. When complete, our conflict is resolved. As I back up, our swept path provides an excellent exhibit to convey the vehicle movement to a stakeholder. Having said this, many times a 2D representation is hard for folks to visualize. To make our presentation more lifelike, we can quickly create an animation. Once created, simple VCR-style buttons allow us to experience our vehicle movements in 3D. While the animation plays back, we can adjust one of several slider bars to control our proximity to the vehicle as well as our point of view. As our SU30 rigid delivery truck turns and enters the drive, we can easily see the effects of the overturn maneuver we assigned in our swept path analysis. With a single click, we can adjust our display to that of the driver's view, and then back to a fixed position camera. The visualization tools within Autodesk Vehicle Tracking provides a means to analyze and present our vehicle maneuvers from any vantage point our project requires, even if that includes the driver's side mirrors. Using the side mirror viewing option, we can experience exactly what the driver will as they reverse into the facility's loading bay. Whether it's a 3D visualization or a 2D exhibit, Autodesk Vehicle Tracking provides the tools necessary to create both very quickly, giving you the flexibility to leverage whichever best meets your project needs. Let's switch gears for a moment and talk next about parking lot layout. As we move to the east, we see a large parking area in need of striping. Now when striping a lot, we want to maximize the number of parking stalls while still maintaining something that is operationally functional. In other words, we can't get crazy. Now laying these out was something I used to do a lot of, and it was an exercise in both art and science. Ultimately, I needed to optimize the layout as well as maintain a geometric standard with respect to stall width, driving aisles, and handicapped spaces. Unfortunately, most lots were usually a unique shape, and the process of figuring out what works best was a time-consuming and tedious process. For example, if I were to ask what is the best striping configuration for this particular lot to net the most usable parking stalls, how long would figuring something like that out take? Fortunately, using our solution, we can figure that out pretty quickly. We will begin by selecting a parking standard, and like the vehicle library, we have a number to choose from. For our project, I will choose a US standard. Having said this, I'm going to choose it from a standards library I made myself. Now let me explain. In our world, trees are green, fire hydrants are red, and unfortunately, parking stripes are yellow or white, neither of which shows up well with the light background I'm currently working with. Because of this, I copied the US standard and changed the stripe color value from yellow to orange. Now there are two things that are important about this. First, you can't change a design standard. And that's a good thing because it's the standard for a reason. However, you can create a copy of a standard and make adjustments as you need to. In other words, if there's not a standard for vehicle, parking, roundabout, or otherwise within our solution that matches your specific situation, maybe you're doing something for a local municipality that has their own, you can start with a copy of an existing standard and then modify it to meet your needs. And once again, in my case, I altered the US standard and added the LB to the end for light background. After confirming my choice, I can begin to lay out my parking bays. I'll start by traversing around the entire perimeter of the lot. And I'll do this by quickly clicking on the endpoints of each segment, whether those be lines or curves. Once finished, I will click to the inside to confirm I only want stripes on the interior of what I defined. I will then use the intelligent grips to convert the line segments to arcs where appropriate. Notice as I make my changes, the parking stalls dynamically update while at the same time staying within the rules-based constraints of my US parking standard. Next, we will fill in the interior area of our lot by leveraging the parallel option. Essentially, this tool will create parking bays parallel to what was already constructed, while at the same time maintaining the driving lane widths. When finished, I get a solution, but in this case the irregular perimeter is such that perhaps I'll be better off filling the interior a different way. Using a standard AutoCAD erase command, I'll remove what was constructed and experiment with laying out a new right-of-way parallel to the north edge of my lot. Once created, I will use the intelligent grips to quickly alter my new parking rows configuration to meet the area that I have to work with. Using the grips, we can extend or shorten the row, as well as change the geometrics of the end bays. Once the first one is set, I will return to the parallel option to create the next parking row. I will then alter this one much the same way as I did the previous one, and then repeat the process once more to create the third and final row. As I do this, it is important to note the speed with which I can experiment with different configurations. This can absolutely save a ton of time in coming up with the best overall solution. With my parking rows established, I'll need to start considering the location of handicapped spaces. And I think I'll start by converting some of the bays in the southeast corner near the building entrance. Now, using my tool, it's a simple point and click operation to make the change. Notice as the stalls are changed from standard to a disabled, the geometry continues to update dynamically. And more importantly, it remains consistent with my selected design standard. We'll go ahead and add just a couple more, and then we'll see where we are overall by generating a parking report. Clicking on the report tool displays an instant tally of our parking layout. Looking at the numbers, we have 152 total stalls, 8 of them being handicapped spaces, which represent a little more than 5% of the total. If we would like to further optimize our layout, we can start to adjust things like parking angle. For example, let's convert the parking stalls along the entrance aisle to be 45 degrees and matching the driving direction. Doing this will reduce our total number of stalls, but will make the parking row narrower, which can in some cases provide more space in a tight area. Once again, as we make changes to our layout, we see the dynamic nature of the objects, as well as the continued adherence to our design standards. With the angles altered, let's check and see what impact it has on the overall number. Looking at the report, making our change nets us 10 fewer parking stalls. So to answer our question from earlier, Autodesk Vehicle Tracking takes the tedious and time-consuming task of parking lot layout and turns it into something that is quick and easy. Now so far, everything we've looked at has been from a horizontal layout perspective. In our next example, let's see how we can incorporate elevation into our analysis. In this design scenario, we have a Civil 3D corridor model, and we want to confirm that this very large vehicle can negotiate the intersection successfully from west to north. Now, we've already created a swept path, and at the first glance, it seems to work. I say seems because in our 2D top view, we are only seeing the horizontal solution. Let's look further at how well this design works vertically. We will begin by examining our design vehicle. To do this, we will create a quick profile of the truck used in this scenario. As we review the profile, we can see several important things. First, the ground clearance at the lowest point of the vehicle is less than 6 inches. Next, the vehicle has 2 articulating points at which it will pivot. Now, as we look at our swept path, we can easily see the envelope of the truck chassis and truck body. But it would be really helpful to see more detail about how specifically this truck with 2 pivot points will make the corner. To accomplish this, we will create additional truck symbology along our swept path to make the vehicle maneuver easier to understand. When finished, an important thing becomes evident. As we review the truck symbols, the lowest part of the trailer is directly over the crown of the road, while at the same time the tires are at the lowest area of the pavement. Because of this, there is a possibility our truck will make contact with the roadway surface. To determine if we have a problem or not, we can quickly run a ground conflict report. Running the report will compare our design vehicle elevation to the elevation of the Civil 3D roadway surface. When finished, we'll see our results displayed in our swept path. As we zoom in closer, we can see where and to what extent our vehicle will impact the crown of the roadway. Using the information Autodesk Vehicle Tracking provides, we are in a better position to make the design decisions necessary to resolve this situation. Now, before we conclude with this example, it's important to note that Autodesk Vehicle Tracking has the unique ability to interact with the native Civil 3D objects directly. In other words, none of your time is wasted performing conversions every time you want to run your analysis. Instead, you can focus on your design where your time is better spent. In our final example, we'll see that our solution not only interacts with Civil 3D objects, but can also create them as required. In this scenario, we will use Autodesk Vehicle Tracking to perform the preliminary layout of a roundabout. We will begin by choosing the appropriate design standard. For our project, I will select the US FHA Rule Single Lane Roundabout Standard. I will then verify that my defaults are OK and set my display consistent for use with a light background. Next, I will place my ICD and begin to assign my approach roadways. You will notice as I select each approach roadway, my chosen design standard is used to create all of the necessary geometry. Now, I don't know if you've ever created roundabout geometrics before, but if you have, I'm sure you can see immediately how powerful this tool is. Once finished, a series of intelligent grips are displayed. Using these grips, I can further refine my roundabout geometrics. For example, I can move the center point and all of my geometry dynamically updates. Now, in addition to the updates, we also receive real-time design feedback. Looking at the table, we can see things like fastest path information as well as performance data for each leg of the roundabout. This real-time design feedback is a powerful tool when exploring different design alternatives. Looking at some of the other grips or intelligent grips that are available, I can make changes to things like the offset of my center line. So we'll make some changes to that. We notice we see a dimension as well as real-time feedback. I can come down and change my splitter width. I could come over and change the angle or the my near side radius. Alright, as each one of these changes, all of the geometry dynamically updates accordingly. Not only the geometry, but you also see that signage is automatically placed in the appropriate location. So notice as I bring the edge of my radius back that my yield sign location is automatically relocated. When I'm ready to make more specific changes to my roundabout geometry, I can use the Edit Roundabout dialog. Once the dialog is launched, we'll see all of the parameters that make up my roundabout, and in this case I can look at leg 1, and if we start by looking at the approach, I can see all of the values that I can adjust very specifically, and if I select a particular value, you see in the diagram on the right a glyph showing you exactly the area that that particular dimension will affect. So if we'd like to add a splitter island to our roundabout, I can adjust the values. In this case, we'll leave them at the default. We'll click apply and our splitter island is created. Now, if we'd like to maybe add some other features, I can do it through just some of the buttons that exist within the ribbon. In this case, we can add a crosswalk, and I'll have you take note of the signage. We place our crosswalk roughly 20 foot back from the radius line, and you'll see that the system was smart enough to dynamically move back the roundabout signage and automatically incorporate the crosswalk or the appropriate signage for that at its appropriate location based on our design standard. When I'm satisfied with all my geometrics, I can move to the next step where I will use my results to automatically construct a Civil 3D corridor. We can accomplish the entire corridor construction with literally only a couple of clicks. As our corridor displays, think for a moment about what we've just accomplished. In less than a handful of minutes, we've not only laid out preliminary geometry that conforms to rules-based design criteria, but we're also in a position to begin modeling the results in Civil 3D. This is a very powerful tool that can assist you in exploring numerous design alternatives in order to find your client the best solution possible. We will conclude this scenario with some quick visualization. We'll start by using standard Civil 3D commands to construct a finished ground surface for our roundabout corridor model. We will use this surface to project or assign elevations to our roundabout components. This includes our signage and some of our symbology. With our surface created, we will then alter our drawing settings such that our vehicle swept paths will automatically use the elevations from the corridor surface. Finally, we will create a couple of swept path analysis envelopes. For the first path, I will select a WB40 design vehicle, or essentially a semi-truck, and set it up to move through our roundabout. As we place our vehicle, notice how it intelligently locks onto the roundabout geometry. It automatically knows the path alignment as well as the driving direction. In this case, I would like to see how my design vehicle works moving through the roundabout and exiting to the northwest. I need only click the start and end point, and Autodesk Vehicle Tracking automatically computes the rest. Next, let's perform a similar operation using a standard passenger vehicle coming from the opposite direction, this time exiting the roundabout to the southeast. Once again, it automatically and intelligently locks onto my roundabout geometry, and within 2 picks, the software solution determines the remaining path for me. With that complete, let's go ahead and create a quick animation. As the animation plays back, we can adjust our display between the views of both the truck and the car. I can also see a little bit of bounce as they move down the road. I intentionally did not do anything to further refine my corridor surface such that I could show you that the vehicles are in fact driving along the native Civil 3D geometry. So to summarize, what is Autodesk Vehicle Tracking? Well, it's a comprehensive transportation analysis and design solution for vehicle swept path analysis. And during our demonstration, we used it to take a look at several ways to determine vehicle movement, both forward and reverse, using manual as well as semi-automatic tools. We also reviewed parking tools and how these can be used to expedite the process of parking lot layout. In every case, whether it was dealing with vehicles, parking lot tools, or roundabout layout, Autodesk Vehicle Tracking supported numerous rules-based design criteria and standard libraries. We also saw that these libraries are user-definable to support essentially any design standard. We also witnessed numerous forms of real-time analysis, including design checks, a steering report, ground clearance report, parking lot count, roundabout heads-up design, visualization, and more. As for the business benefit, Autodesk Vehicle Tracking is a solution that's easy to use, intuitive, and extremely powerful. It's also designed to work within a familiar AutoCAD environment. Its numerous features can help you speed the planning and design processes, as well as more quickly evaluate design alternatives, such that you can present your client the best design solution possible.